Okay, so this is section 8.4. It's on hypothesis tests for a population mean again. But this time the population standard deviation is unknown. That's basically how things are in statistics. You really don't know anything about populations. So the notion that you'd know the population standard deviation, again, from the whole population, that's a lot of data that you won't be gathering. You're going to be using a sample standard deviation from your sample. That's a realistic assumption. But you may remember that when you do the standardizing process, which is usually taken as z-score, if you change this and instead you're like, oh, there's no way we're going to know the standard deviation for the population, so you use the sample standard deviation for that. We remember the sample standard deviations vary from sample to sample, and the z-score is no longer called z, it's called t. Okay, because t distribution just allows more variability. It's a wider distribution of outcomes. So that's what happened. The only other thing is, so the t distribution is sort of driven by the standard deviations that vary from sample to sample, and the amount of variability in a sample standard deviations is related to how many of the deviations that are random. One of the things we talked about is deviations from the mean always add up to 0, and that's not, there's something not random about that. In fact, if you have 10 deviations from the mean, we view 9 of them as being random because the last one has to make the total 0. So that's called degrees of freedom. If a sample size is n, then there are n deviations from the mean that add up to 0. So only n minus 1 of them are random, and n minus 1 is the degrees of freedom. For a t distribution, and that's basically what determines the width of the t distribution. Let's go right into section 8.4. Again, this is where sigma is unknown. We're still doing hypothesis tests for a population mean. Okay, so here we go. It says, in this lesson, we study hypothesis tests about a population mean where the population standard deviation is unknown. Here's an example. So the mean roll on a fair 6-sided die is 3.5. So if you think about it, it goes from 1 to 6. 1.6 is 7. You divide that by 2, it's 3.5. So that's the mean roll on a fair die. So you think your favorite casino is using loaded dice. So you very cleverly steal one, forgetting there are video cameras everywhere. At home, you roll the die 1,000 times, and the mean roll is 3.35 with a sample standard deviation of 1.78. Test the claim that the die is not fair using a 1% level of significance. Okay, so there's a lot going on here. You're going to need the sample mean, okay? And if you look back, that's your mean roll of 3.35. So you did not get 3.5. I don't know if that proves the die is unfair until I see how many standard errors that is from what it should have been, which is 3.5. Okay, now the standard deviation you're using is a sample standard deviation, which is 1.78. Okay, and the sample size was 1,000 rolls. Okay, and then you have to check the condition. Oh, let's get our alpha. The alpha is 1% over here, 0.01. That's again the level of significance. Okay. The check, remember, you have to check, same thing, sample means have to have a normal distribution. So sample means are normal if your sample size is bigger than 30, or the population you're sampling from is normal. So check in greater than 30 and, or population is normal. Gotta always do that. So here are in 1,000, certainly bigger than 30. So, and I know that rolls on a die are not normal. If the die is fair, then the probabilities are all the same. They're not bell-shaped. So it's not normal, but as long as your sample size is bigger than 30, then the means will be normal, which is the activity we did in class last night. You know, we had a dice, we had a simulation of rolling dice and computing averages, and we just saw how the distribution of outcomes always comes out bell-shaped. Okay. But otherwise, so this is the same as the last section. Your null hypothesis and the alternative hypothesis are with regard to the population mean. Okay? And we're assuming the die is fair, which means the mean is 3.5 for the population. You only rolled a sample of rolls, and we did not get 3.5. We got something different. So the alternative hypothesis is that the mean is not 3.5. That means the die is not fair. Okay. Any questions? Is it a two-tailed test? Not equal means less than or greater, so that's left tail or right tail. Now, our test statistic, just keep in mind that, again, it was a z-score. I'm going to change this. Okay, x bar minus mu over sigma divided by the square root of n. Sigma is the population standard deviation, which is unknown, so I'll erase that and replace it with the estimate, S, the sample standard deviation. Those deviations from the mean add up to 0, causing a t-distribution with n minus 1 degrees of freedom. We call that t. Again, there are n deviations from the mean, but only n minus 1 of them are random. Sample standard deviations vary from sample to sample, which gives a distribution of outcomes that's wider than a normal distribution. So we have to look up our t-distribution. Oh, let's go ahead and compute this real quick. So the x bar was 3.35. We're assuming the mean is 3.5 in the null hypothesis. Okay, using a sample standard deviation of 1.78 and divide by the square root of the sample size, which is square root of 1,000. Okay, so go ahead and run that. Okay, so yeah, thanks, Andrea. So it's negative 2.66. Okay, I'm gonna later we'll round. You see, we're gonna have to round to negative 2.7. Okay, and that's a big rounding, but we're forced to, so I'll talk about that in a second. Okay, now we have to do our critical value. So the critical value, remember we do CV for that, table A2. This is where we use degrees of freedom for t statistics. Again, there are n deviations from the mean in the sample standard deviation. Only n minus 1 of these are random, and that determines the width of the distribution. Our alpha is, what is it, 0.01. And this is a two-tailed test, as we said before. All right, so let's check that again. 0.01, two tails, how many degrees of freedom? It would be 999, I guess. That's not going to be in the table. So we'll just pick the closest we can find from that. So let me grab, again, table A2. So there's 1,000 degrees of freedom in the table. You just pick the closest one you can find. Okay. If it gets much bigger than 1,000, it becomes a Z distribution, as we talked about before. Okay, so again, our alpha was 0.01. It's two-tailed, so that's the first column here. So I hope you see it as we're doing 1,000 degrees of freedom. So it's 2.581 here. Okay, again, that was with a 0.01 alpha two-tail. 2.581. Okay, so I'll put that in here, 2.581. Any questions? Maybe a little picture of that. Remember, this is a two-tailed test, so for the critical value, it's a plus or minus. It could be in either direction. So again, it's a t distribution. So I'm going to put a 2.581 down. And a negative 2.581 on the other side. And that's the definition of statistical significance right now. If it goes beyond that and under one of these tails, that's statistical significance. So we get a negative 2.66 for our t value. And so that's going to go right in here. And because it's in the tail, we call that statistically significant. Okay. Any questions to this point? Okay, and now we can do a p-value. This one's a new table. So table A3 is where you have to round your test statistic. So table A3 is p-values for the t-distribution. We've never done this before. We've done critical values with the confidence intervals, but we've never done p-values. So you needed a new table for that. So the way the table works, is it does degrees of freedom along the top row. So you got to n-1 for that. And then you have to do your test statistic down in the first column, okay? And the t needs to be rounded to the nearest tenth. Okay, so that's why I was saying we'd have to take that negative 2.66 and round to a negative 2.7. There. The degrees of freedom are still 999, so you use the same thing there. And again, just pick the closest one. This table's not going to have 999 degrees of freedom. Okay. Okay, any questions? Let's grab the table real quick. Again, it's A3. And this is a this is sort of a dense table. Yikes. What did I say? Negative 2. Oh, I lost. Negative 2.7? Yeah. So there's a place for negative values or positive. So negative 2.7 is on the second page of the table. And I see it here. And I'm going to go way out. I have to have 1,000 degrees of freedom, which we'll just call infinity because it's much bigger than 100 degrees of freedom. So I'm basically in the last column of the table. With large degrees of freedom, the t-distribution approaches the normal distribution. So these are actually normal distribution p-values with infinity degrees of freedom. Okay, so I want to zoom in on this one real quick. So the infinity symbol is a sideways 8 up here. Okay, so that's infinity degrees of freedom, which is the best we can do for 999. And so you see p-value is 0.0035. And this table works just like table A1. It gives areas to the left of a z-score. So this is 0.0035. Let me draw that real quick. Like that. Okay, and then the graph, you have to remember this is a two-tailed test. Okay, so you're counting both sides of the distribution when you do two-tailed tests, which just means you get this area and you have to double it, okay? So it's a t-test, I'll put a t down there. My z-score is a negative 2.66. I'll put a negative 2.7 just to be sort of clear here. I used a negative 2.7. And the area we got, oops. So the area we got was 0.0035. That's not the p-value, because you also have to count the right tail. P-value is probability of getting at least this extreme, and on a two-tailed test, it's in either direction. Okay, so just all you got to do is just double it. So the p-val is 2 times 0.0035, which is 0.007. You can add a 0 if you want after that. Okay, I'm just going to pause for a second and see if we have any questions. Okay, and then it's the same as before, the conclusions. Let's see if I can just paste that back in there. There it is. P-value is less than or equal to alpha. You reject the null hypothesis and support the alternative. So after doubling it, the p-val is 0.0070, which is less than, I think it's 0.01. Let me double check this. No, yeah, and that's alpha, which means we're going to fail to, we're less. So we're going to reject the null hypothesis and support H1. And remind myself, H1 said that mu is not something 3.5, oh yeah, the die, it's a die that's not rolling a 3.5 average. That's a loaded die. At least that's what our data say. Any questions? So somehow write this in with plain language. The data support the claim. The die is not fair, which is another way of saying the mean roll is not 3.5. Okay? And we'll pause for any questions. Okay, so again, that's the third test we've done for a mean. The only real difference is that we use a different distribution for the p-value, different table for the p-value. So it's a little bit of a curveball, but otherwise it's the same as the previous lesson. Let's do one more. So let's go up to the last example here. Oh, here it is. I just kept wondering where I'd see this problem. And I remember my dad bought a house once. It was really old, and the windows were sort of runny looking, meaning even if you clean the glass, you could see sort of drips in the pane. And lots of people have said that glass is actually a super thick liquid, that if you leave glass vertically long enough, that the glass will start to drip. It starts to run toward the bottom of the window. And I spent some time on Wikipedia, and I learned that the glass is what they call an amorphous solid. So it's sort of a solid, but does that mean it'll drip like this? So let's go ahead and read this problem here. It says, a cathedral in Europe is over 500 years old with hundreds of panes of glass. The panes were originally manufactured to be 0.25 inches thick, but now the bottoms of the panes appear to be slightly thicker. So the glass is running to the bottom. A random sample of 125 windows were measured at the bottom, and the mean width was 0.256. So that's a little wider with a sample standard deviation of 0.031. So is that random, or is it really thicker at the bottom? We know it's thicker on average just for these windows, but it's not all the windows. And I can't decide if this is sort of a random thing or if it's real. So let's test the claim at a 1% significance that the mean thickness at the bottoms of the windows for all the windows is bigger, sort of thicker than how they were made, which is 0.25 inches. Or could this just be a random thing that happens with random data? Okay, so the sample data first will be X bar. That's the mean thickness, which was 0.256 inches. Sample standard deviation is 0.031, that's S. N, the sample size, is 125. Remember, this has to be bigger than 30, so that's my check. I'll just do a little check mark there. My alpha is 1%. It says 1% significance, so 0.01. Any questions? Now, we're just testing the claim that the mean is bigger than 0.25, even though they were manufactured to be 0.25 thick. The alternative hypothesis says the mean is bigger than that now, bigger than 1/4 of an inch thick. Any questions? Okay, and that's the last statement here. You can usually find the alternative hypothesis in the question if you look for it. And regularly, we don't state the null hypothesis. So we know that with the null hypothesis, you take the alternative and change the inequality to an equal sign. U equals 0.25. That's all you have to do. Any questions? So the test statistic we've talked about, this is a t-statistic. So it's x bar minus mu over s divided by the square root of n. We are using a sample standard deviation, which varies. Population standard deviation doesn't. Using a sample standard deviation makes the distribution wider than a normal distribution. That's the t-distribution. All right, our x bar was 0.256. Minus the population mean, that's 0.25, at least we're assuming it is, over standard error, which is s, 0.031, divided by the square root of n, that's the square root of 125. Okay, so go ahead and run that computation. Let's see if we can agree on it. Anybody get that? Good, thank you, 2.16. And again, we'll round to 2.2 later. Just as a reminder. Okay, now we need that critical value. That's the table A2. So for degrees of freedom, that's n minus 1, which would be 124. Okay, on this one, I think our alpha was 0.01. Double check. 0.01, and it's a one-tail test. If you look at H1, this tells it's a right-tail test. Okay. So our alpha again was 0.01. Make sure you do this under one tail this time. You will not find 124 degrees of freedom. Pick the closest one you can find. Okay, so let's go over there. 124. This is, did I screw this up? No, this is great. So this is table A2. So we'll have to do 100 degrees of freedom on this one. And it's a 0.01 one test. That's the second column. Okay, so again, 0.01, one tail, second column, takes you down to, with we're doing 100 degrees of freedom. Because 124 2.34 is what we want, and that's obviously closer to 100 than it is to 250. So we're going to use a 2.364 for the critical value. Any questions there? Again, this is table A2. 2.364, is that what it said? That's how fast I would forget things. 2.364. I just don't know. Yeah. Okay. And so maybe you can draw a picture. Remember, this is a right tail test, so there's no two tails. 2.364 is what we got. And this is our definition of statistical significance here. Actually, the tail may be better than that. And the area of the tail is alpha, so alpha is 0.01. And our test statistic is 2.16, so this is down here. Because it didn't make it to the tail, it's not significant. Okay, so I want to pause and let you guys see if you have any questions about that part. So again, the 2.364, that's the critical value. We just say CV on that. And this is the rule for significance. And we got 2.16, but it's not good enough. Any questions? Almost done. Okay, now a p-value. This is table A3. Okay, so for degrees of freedom, again, that's n minus 1. And again, n is 125. So n minus 1 is 124. Our test statistic was our t-score, which came out to 2.16, and I'm going to round to 2.2 now, because you have to. Okay, so 2.2, 124 degrees of freedom is what we're trying to find in the table. Remember, these tables give areas to the left, and also remember, this one's a right tail test. Okay, so we're gonna have to tweak this a little. All right, area to the left, again, table A3, 2.2, 124 degrees of freedom. We're gonna go to the positive side. Okay, see the 2.2 down there. 100 degrees of freedom is the second to last number in the table. All right, here we go, 2.2 right there, and then all the way out to the end of the table. Okay, so again, 2.2, and then 100 degrees of freedom all the way down is the second to last column here. Okay, so when you zoom in, you should see 0.9849. That's the area to the left of the test statistic, 0.9849. Maybe draw the picture. So the test statistic was 2.16. I'll just put the 2.2 now. The area the table gives is 0.9849. That's the area to the left. These tables only give areas to the left. Okay. And the p-value, being a right-tailed test, needs to be the area to the right. Okay, so here in this case, because it's a right test, you have to do 1 minus the area to the left. And see if somebody's got that. Not yet. Thank you. 0.0151. And that's going to be bigger than our alpha value. So let's see if I can get lucky and have this here one more time. There it is. Okay, so the p-value 0.0151 is bigger than 0.01, which is alpha, which means we fail to reject the null hypothesis. Or in this case down below, second case. Don't reject the null hypothesis or fail to reject. Remember, we never support it. We don't reject it, but we don't support it. Fail to reject the null hypothesis, which said that the mean is 0.25. Don't support the alternative. You can only support the alternative if you reject your assumption. So don't support HA. It said the mean thickness is greater than 1/4 inch. Huh. So the bottom of, based on these data, the bottom of the windows did not get thicker. What that says. So we'll conclude by saying the data do not support the claim. That the mean thickness. Bottom line is, see, you get this mean thickness. It was bigger than 1/4 inch, but not significantly. So you just say, oh, that's random. Okay? Remember, you only sampled a small number of windows. Okay, so the mean thickness at the bottom of the windows, I'll say the bottoms, is greater than 0.25 inches. Okay. Okay, that's it. Now there's a, we're obviously not going to do this next lesson. What I want to have you do is I'm going to have you guys look at type 1 and type 2 errors in section 8.1, and I'll talk about it next time. So I'm just going to put a note down here. Please, you can look in the index for this. So please read about type 1 and type 2 errors. In 8.1 before starting the homework. But I want you to go ahead and start the homework, okay? It's just like the medical testing we keep hearing about with COVID-19 right now, that the tests are not perfect. They use data to make decisions just like us, and sometimes the decisions are wrong. So remember, in medical testing, they have false positives and false negatives. So a false positive is when they say you're sick but you're not. And that's actually not as bad as a false negative, where they say you're not sick but you are, because then you're going to go around and infect people. In statistics, we call those type 1 errors, and type 2 errors is basically the same thing. You make one decision, you say yes when you should have said no, basically, or you say no when you should have said yes. Type 1 and type 2 errors. And it turns out, and we'll talk more about this, but the value for alpha is related to the probability of a type 1 error. And so you can actually manage the probability of a type 1 error in the way that you choose alpha. And it also affects the probability of a type 2 error as well. So we're going to talk about that next time. But again, that's in 8.1, which is in the extra credit section. But I'd like you to just read that discussion. And again, you can just look it up in the index in the back of the book, or just kind of skim through 8.1 until you find it. But I will talk about it next week. It's just, I think it'll come up in your homework in this chapter. So, and you should know, you really have to know about it. So, okay. Any questions before we quit for the day?